You need to be able to prove all three of these Pythagorean identities. Now, this one is in the AS, and these aren't because they use the reciprocal functions sec, cot and cosec. So if you're a first year student, don't freak out about sec, cot and cosec. I'm going to put all these together because by the time you get to the end of the second year, you'll think of them all together. But you only need this for the first year. You don't need these two, okay? As well as the three Pythagorean identities, there's also 3 addition formulae, 5 double E half E angle formulae, and 2 half E double E angle formulae. So second years, you've got all this to learn. First years, oh, you've just got that one, so be grateful, okay? So we're going to prove all 3, but if you're a first year, don't worry about these second 2. Right, we're going to come back to the definition of sine and cos. We've got a unit circle. This is the angle x. This is cos x down here on the adjacent side, and this is sine x here. Now, pretty much I've already proved it, haven't I? Look, it's obvious, Pythagoras. That squared plus that squared is that squared. Sine squared plus cos squared is 1. Done. But I'm going to prove it using the definition of sine and cos in terms of the triangle. So, sine squared x plus cos squared x. Well, sine is the opposite over the hypotenuse, and cos is the adjacent over the hypotenuse. When you square a fraction, you square the top and you square the bottom. When you add fractions, you make the bottoms the same and add the tops. Okay, let's refer back to our triangle. We've got an angle, an opposite, an adjacent, and a hypotenuse. Use Pythagoras, you see that h squared is o squared plus a squared. So therefore, this is h squared over h squared, which is 1. Actually, I should write that here because of the structure of proof. Not there. That looks much better. And there you go. There's a proof. So there's lots of different proofs. You could just look at that triangle, to be honest, and say, well, if that's the definition of sine and cos, then obviously by Pythagoras, sine squared plus cos squared is 1. Now, we're going to use sine squared plus cos squared is 1, and we're going to use it to prove the other 2. And I'm just going to reference, because I just did it myself, one of the little warning things with these identities, which is don't write them without an angle. We all say, if your teacher says tan squared x plus 1 is sec squared x and sine squared x plus cos squared x is 1, they're a really good teacher, because I don't know anyone that says that. We can't be bothered. We're too lazy. We say sine squared plus cos squared is 1, and that doesn't actually make sense. You must have an angle. Otherwise, you can't have sine. Sine of what? So don't write sine squared plus cos squared is 1, even though we say sine squared plus cos squared is 1. Sine squared x plus cos squared x is 1. Now, what you're going to do is you're going to divide each term by sine squared x, okay? And then that's basically going to be it. So we divide this by sine squared x, we divide this by sine squared x, we divide this by sine squared x. Okay, this is clearly 1. This is cos over sine. See, I did it again. Cos x over sine x squared, because the top's being squared and the bottom's being squared. And this is 1 over sine x squared. The top's been squared, bottom's been squared. Now, cos over sine is 1 over sine over cos. So this is 1 over tan, and 1 over tan is cot. As I said, if you haven't done reciprocals, don't worry about this. And 1 over sine is cosec. There we go, done. And guess how we're going to do this one? Yes, you are right. Well done. We are going to divide each term by cos squared x. Cos squared x. So hard. It doesn't matter when you're thinking it and saying it, but when you're writing it, you've got to put that angle in. Right, you get divided by cos squared x, you get divided by cos squared x, you get divided by cos squared x. Sine squared over cos squared is sine x over cos x. I think I just did it again, actually. Oops, sorry. Sine x over cos x squared is sine squared x over cos squared x, because the top is squared and the bottom is squared. Cos squared x over cos squared x is 1, and 1 over cos x squared. Sine over cos is tan. See, did it again. Sine x over cos x is tan x squared, plus 1 is 1 over cos x is sec x squared. There we go, proven. Now this is my favouriteest way of you remembering them. You write a tan here, and then tan is sine over cos. You can write it in that order. and then opposite each one is its reciprocal. Cot, reciprocal of sine, cosec, reciprocal of cos, sec. Notice I'm breaking my own rule again by not putting an angle. This is the trouble. It's a rule, but no one follows the rule, and then you're supposed to follow the rule. Put squares on them all and put a 1 in the middle. Now everybody knows that sine squared plus cos squared is 1, by which of course I mean sine squared x plus cos squared x is 1. So this is really easy to remember, that arrow. Sine squared plus cos squared is 1. And the nice thing is about this is that round the hexagon, the same shape arrow appears. Tan squared x plus 1 is sec squared x. 1 plus cot squared x is cosec squared x. And this is a really, really good way of remembering them. It's my favourite, magic hexagon. It's not really magic, is it? But that's what people call it. The other thing is that I want to point out is that trig requires experience. Okay, you are not going to be good at this straight away. You need patience. Okay, don't freak out and don't think you're rubbish at it. It takes a long time to get good at it. But for now, what we're doing here is just memorising these 3, and I recommend that you use the hexagon. My last comment about what not to do is don't rearrange these 3 in your head. Looks simple, doesn't it? All I have to do is move that to the other side and I get tan squared is sec squared minus 1, but it goes wrong. So when you need it to say sec squared equals, or you need it to say cot squared equals, or cos squared or sine squared, just write it down and do it with your pen. It makes it much less likely to go wrong. Now, the Pythagorean identities you use more than any of these. Okay, this is used the most. I'll tell you the times when it's used. We might know sine x and want to know cos x, but we don't want to find out what the actual angle is. So if you think you can rearrange this, can't you, to say cos x equals, and then you could sub in what sine x is and find out what cos x is. You might be solving an equation or doing a trig proof. Obviously, that would be a time when you'd need the Pythagorean identities. You might be converting parametric function. This is A2 stuff now. AS, this is going to be A2, A2. Parametric conversion to Cartesian. You might be doing that, in which case you're probably going to need the Pythagorean identities. And you might be differentiating an inverse function, in which case you're probably going to need the Pythagorean identities. So if you're interested in seeing how they get used, have a look at differentiating inverse functions and have a look at the parametric functions, and you'll see how we use this magic hexagon a lot. But in terms of the first year, you're just going to be solving equations and doing trig proofs and possibly doing this, just using that one. And the main thing in the second year is doing these things with all 3 of these identities.